Okay, students, we are going to be looking at section 7.4. So we're going to be looking at the idea of permutations and combinations. Before we get into that, we're going to learn a little bit about what a factorial is and kind of learning how to work with those. Factorials have a lot of application when we're talking about counting principles in permutations and combinations, so you need to know what we mean by a factorial. So what a factorial is it's represented by just the exclamation point, and it just means, for instance, this would be 4 factorial, you're going 4, 3, 2, 1, and you're multiplying. 8 factorial, 8, 7, 6, 5, 4, 3, 2, 1, and multiplying. And these numbers get really big. You'll kind of see at times overflow in your calculator when you put too big of a number in. A couple of things that are important is 0 factorial by definition is 1. So that's just something that we have to define so the formulas we're going to be working with work correctly. And 1 factorial is also defined to be 1. Okay, so that's the idea of a factorial. This formula right here is just saying, okay, like if n was something like 5, then you just go 5, then you go 5 minus 1 or 4, and then you go 5 minus 2 or 3, and so forth. Okay, so that's the idea. So what we're going to do is just work some of these out. I'll also get my calculator loaded up here and show you how you can do this on a calculator automatically. It's kind of nice. So hold on just one second. Okay, so like magic, my calculator appears, so I want to show you where you can do this. All right, so to begin with, let's just crunch some of these out. 5 factorial, again, would be 5 times 4 times 3 times 2 times 1. And you could, of course, just put that in your calculator like this, but I'll show you the fast way here in just a second so that you don't have to do this all the time. Of course, it doesn't matter when you do the 1. So that's equal to 120. 3 factorial would be 3 times 2 times 1. So that would be 6. All right, and then what did we say 0 factorial was? We said by definition that's 1. We said by definition 1 factorial is 1. Okay, so those are two are by definition. So let me show you how we can do these on the calculator. So first of all, you want to go enter the number. So let's go down and just kind of do these together. So you go 10, enter the number. Then you press the math button. Then you go over to where it says PRB or PROB on my calculator, like that. Then you find option 4, and you just press enter. So that's how you get 10 factorial to come out, and gives you a big number. So I told you these numbers get real big real fast. So this is 36288. 00, so you put your commas in the right place. That is 3,628,800. Okay, let's do 50 factorial. Again, what you do it in your calculator. 50 math prob 4. Okay, option 4. Let's get that to come out, press enter, and see now you get into scientific notation. So we'll just round this. We'll just say 3.04. And when you see that E64, that's saying times 10 to the 64th power. If you need a review on that, all that really means is that decimal gets moved to the right 64 places. So that would be a really, really big number. I don't know exactly what that would be, but you're just multiplying or moving the decimal over 64 places. Okay, now let's go 100 factorial. All right, give this a try. Show you what happens. So we go 100, and then again we go math, PROB, option 4, and look what happens. You overflow. Okay, so the answer is not overflow. It's just we don't know what the answer is. Okay, you'd have to have a much more powerful computer to work that out. You can have a supercomputer, and that would figure that out. So yeah, that does overflow the calculator, so you can't do that. I think when you get up to around 60 factorial, somewhere in there, that's where it tends to overflow. I can't remember exactly, it doesn't matter. So I'm going to just try that just out of curiosity. 60 factorial. Yeah, see, that's up to the 81st power and so forth. So it only goes up to the 99th power in scientific notation on these calculators. Okay, now what we're going to do is do some computations with factorials. These things could be put in the calculator, but I want to show you a little technique that you want to know how to do for simplifying these. So we could do 20 factorial and 17 factorial on the calculator, but I'm not going to do this. I'm going to show you what I'm going to do. I'm going to start writing out the 20 factorial. So we know that would be 20 times 19 times 18 times 17. And then we could keep writing that if we want to, but we really don't need to. And here's why. Okay, from here it would be 17, 16, 15, 14. You can just put a factorial in there and leave that alone like that. And then you can leave the factorial the way it is like this. And then those things will mark themselves out. Okay, then you can take your calculator, and when you do that, you can do it this way. So you just go 20 times 19 and then times 18 and times, that's it, 20 times 19 times 18. And you, whoa, what in the world did I do? Did I miss something there? Oh, I got the extra sign there. There we go. Okay. All right. So the answer to that problem would be 6,840. Now, see, you can do this on your calculator like this. You could do this. You could go 20 factorial. Okay, like this. Oh, teacher. Dang it, I'm losing my eyesight. Okay, so I got 20 factorial, which we could put in. Okay, then we could go divide by 17 factorial. All right, you could do it like this, okay? But I want you to know how to do this both ways, all right? So it's good to know how to write those things out like that then. So that would be how you could do that, all right? Okay, I prefer you know how to do it this way and then check on your calculator, okay? So the next one goes like this. We're just going to leave the 9 factorial the way it is, leave the 4 factorial the way it is. Now that's implied multiplication, and 9 minus 4 is 5. So that's 5 factorial. So what we're going to do is write this out. So we're going to go like this. I'm going to go ahead and start writing the 9 out. So I just go 9 times 8 times 7 times 6. I don't need to write it out all the way because I'm going to want that 5 factorial to cancel out. So instead of going 5, 4, 3, 2, 1, leave the factorial in. And then you could go ahead if you wanted to and write the 4 factorial out as 4 times 3 times 2 times 1. And then leave the 5 factorial alone. So the idea is that'll get those things to cancel out. And then, of course, you could go to your calculator. I'll show you one other thing you could do. Like, notice 8 and 4 is 2. So you could do that if you wanted to. 6 and 3 is 2. You could do that, or you could do 9 and 3 is 3. It doesn't make any difference. Okay, I think I'll just go like this. 6 and 3 is 2. Like that. All right, so it looks like what we're left then is this. We just could now go to the calculator and work this out. So let's see. In the top, what we would have left over is we would have 9 times 2 times 7 times 2, like that, and that would be 252. Okay, and then what we're left with in the bottom is everything canceled out except the 2 times 1, and then you could just divide that on your calculator if you wanted to. Okay, so we get 126. All right, and that would be the answer to that problem then. Okay, all right, now could you do this in your calculator? Yeah, you could. I'll show you how you could do that. You could go 9 factorial, like that, okay, and then divide by. Now, you have to do this kind of carefully in parentheses. you would need a big set of parentheses to enclose this. So you would have the 4 factorial. And then if you wanted to, you could do another set of parentheses like I did here and do 9 minus 4, close parentheses, math, probability, and then the factorial like that, and then close parentheses like that. So I've got that put in correctly. I've got the 9 factorial, 4 factorial, 9 minus 4 factorials in parentheses. You could do that, and you get 126, okay? So how do I like you to be able to do that? Really both ways. I'd like you to be able to do that. Probably what we're going to learn how to do mostly is learn the permutation and combination formula, which is what this is showing as a combination formula. Okay, so let's go to the next page. I'm going to let you all work on these 4 problems a little bit. You'll need to use your calculator some, but try to do as much of this as you can without a calculator, all right? Try to do the cancellation and that kind of thing. That's the way I'm going to do that. So pause. When you're ready, check and see if you're doing okay. Okay, so let's go ahead and let's check and look over what you did and see if you got these right. So I'll show you how I'm kind of wanting you to be able to do these is write these out before you go to your calculator. Every one of these things could be put in your calculator without having to do anything. So I did the 12 factorial. I wrote it out as 12, 11, 10. Then I stopped at 9 factorial so it would cross out that 9 factorial. So you end up with 12 times 11 times 10. 12 times 11 is 132. 132 times 10 is 1320. Okay. And then the next one, I went ahead and worked inside the parentheses to make the 6 minus 3 factorial 3 factorial. So I wrote out the numerator as 654, and since I knew I was going to cancel out a 3 factorial, that's why I stopped there, because 3 times 2 times 1 is 3 factorial. It doesn't matter which one you cancel out, so I just left that one alone, and then I wrote this one out as 3 times 2 times 1. That cancels that out. Now, if you wanted to, you could just do 6 times 5 is 30. 30 times 4 is 120. 3 times 2 times 1 is 6. Divide that out, so you should have got 20 on that then. And then the next one, yeah, you could take your calculator if you did it this way. There's not a thing wrong with doing it this way. If I did 12 times 11 times 10 times 9, you could have, and I'm sure some of you did it this way. It's not wrong to do it this way. You could do that, and then the bottom is, 24? So if you did it that way, you'd still get 495. I just decided, well, let's just see how much this we can do in our head. Okay, so 12 over 4 is 3. Let's see, what else did I do? I did 10 over 2 is 5. 9 over 3 is 3. So I just did 3 times 11 times 5 times 3. Okay, the next one's real simple. The 21, you write 21 instead of going 20, 19, 18, blah, blah, blah. You just want to stop at 20 factorial so those things will cancel out. So then you've got 21 as your answer. All right, so hopefully we did okay on that. All right, so the next thing we're going to do, moving on to part 2, is we're going to look at what we mean by a permutation. And we're going to look at permutations, and we'll look at also the idea of a combination in this section today. All right, so a permutation of a set of distinct objects, it's an arrangement of objects in a specific order without repetition. So I'll explain with some examples what we mean by that. Okay, so here's kind of the idea. This example 2 says, how many ways can 4 different books be arranged on a bookshelf? Okay, well, what you have is, let's just say, okay, I got 4 books that I can choose from. Okay, and I'll just label these like A, B, C, D. You don't have to draw this out. I'm just kind of showing you my thought process. Well, the idea is this, okay? When you pick a book and put it in this location on the bookshelf, you have 4 choices. Okay? Now, it doesn't matter which one I pick. Let's just say I picked C. Okay, so after I pick C, how many are left to put here? Okay, yes, there's 3 left over. Okay, so let's say that we picked book B. How many are left over? There's 2 left over. Okay, and then that one's on the bookshelf, so we got 1 left. So what you're doing is you're doing the multiplication principle here to find how many different ways you could arrange those books on the bookshelf. Because for every possibility here, there's all these possibilities there. Okay, then you just go to your calculator. 4 times 3 is 12. 12 times 2 is 24. So it turns out there's 24 ways to do that. Now, we learned how to do tree diagrams. A tree diagram on this could be done. I'm just going to show you, and you don't need to write this down. I'm just going to show you, without drawing the entire tree diagram, what we're doing. Okay, just so you get the idea here, all right? Well, the first place you could pick any of the 4. Now here, you could pick anything but A. You've already picked A, so you could pick B, C, or D, like that, okay? I'm not going to go do this, but these things would be branched 3 times like that. I'm not going to fill out the details. When you go to the third book, well, this one could be, it couldn't be A or B, so it could be a C or a D. This one couldn't be an A or a C, so it could be a B or D. Okay, and that's what would happen when you get to the 4th book. Well, this branch right here would be A, B, C, D. Now, I want you to just kind of think about what the tree diagram is doing. Ultimately, you're going to end up with 24 branches. Okay, a person could figure this problem out with a tree diagram, but it's complicated to draw those branches out. But if you think about this, you would have 24 branches, because what you really have is you have 4 here, 3 here, 2 here, 1 there. Okay, so if you filled that out completely, that's what you would end up getting. Okay, so it's a lot easier to do this. So that's how that problem works out. Okay, the next problem says, in how many ways can the digits 0 through 5 be used in the 6-digit combination lock if the same digit can never be repeated? Now, we've talked about that before. So the idea is you have these 6 digits to choose from. So it's very similar to the bookshelf problem. Okay, the very first digit could be any of the 6. But the same thing would happen. Let's just say we chose a 0. Okay, well, now there's 5 things left over. Okay, now let's say we chose the 4. Now there's 4 things left over. And let's say we chose the 2. Now there's 3 digits left over. And so forth. We chose a 5 or whatever. Now there's 2 left over. Okay, and we erase that one. There's only 1 choice left over. So we got that. It's the same idea. So see, this is looking a lot like a factorial, isn't it? Now this one you'd probably want to do on the calculator maybe. So it'd be 6 times 5 is 30, times 12, times 2. So that would be 720 ways to do that. Okay, and the idea is you can't repeat. So it would be wrong to have a combination 0, 0, 1, 1, 2, 2. You can't have that. None of the digits can be repeated, see. Okay, so that's the idea. Okay, so if you look at this, then this is really 4 factorial, and that is 6 factorial. That kind of gives you an idea why we talked about factorials, because it has a lot to do with these counting problems, okay? So in a permutation, you may not repeat, okay? And this is wrong. Order does matter. Shame on the teacher for putting that there. God, that's a bad mistake. Okay, so order does matter. All right, now we'll talk about what that means in just a minute. You know, the idea on that would be like for the books, okay? A, B, C, D is different than C, B, D, A. That's a different arrangement on the bookshelf, so that order matters. Okay, we'll kind of talk about what it means for order not to matter a little bit later here. Okay, so here's the idea. We're going to look at a number of permutations of n objects. So the number of permutations of n distinct objects without repetition. You're not allowed to repeat in a permutation. denoted by NPN. So that's written like this. And what that means is just a factorial. All right, so that is n factorial. That's kind of what we got on here. That one ended up being 4 factorial and 6 factorial on those two examples I gave you. So as an example, the number of permutations of 7 objects would be notated this way. And that we know that's 7 factorial, 7, 6, 5, 4, 3, 2, 1. We know what the factorial is. So that's how you represent that then. Now, what we're doing is we're choosing from, if you go back here, we're choosing from 4 books, but we're putting them in 4 positions. This one we're choosing from 6 digits, and we're putting them in 6 positions. So this one up here, you could think of this as a permutation 4-4, and this would be a permutation 6-6. So that's just what the notational system is that we use, okay? All right, then the next thing is we have a permutation of n objects taken r at a time. A little bit different idea, so I'm going to use this as an example, okay? I'm going to pause just for a second and come right back. Okay, so we're going to work with a tree diagram on this that'll kind of help us get an idea. So we got a set of letters, X, Y, Z. We're going to find how many permutations are possible for this set of 3 objects taken 2 at a time. All right, so it's going to go like this. To begin with, we're just going to look at the first letter. So we're just going to, of course, we have 3 things to choose from. So we could either have an X, or we could have a Y, or we could have a Z. Okay, so we know that. And then when you go to the second letter, well, remember, we can't repeat. So once we have chosen that X, the only thing left over is either a Y or a Z. Okay, and same thing here. If you've chosen a Y, the only thing left over to choose from is a X or a Z. And same thing here. If you chose the Z, what's left? X and Y. Okay, good. All right, so we got that. So that would be how the tree diagram goes for what we would say 3 objects taken 2 at a time. And there's no repetition. When we're dealing with a permutation, we can't repeat. So we couldn't have XX or ZZ or YY. We can't have that. Because once you take it out, you've used it up. Okay? So how many possibilities are there? Well, there's 1, 2, 3, 4, 5, 6 ways for this to happen. Okay, so the idea is, let's list what those possibilities are. We just read from left to right. So you would have XY. That would be one possibility. Then XZ. Then YX. Then YZ. Then ZX. And finally ZY. So those are the distinct possibilities that you get in there. So what we're going to do is we're going to just kind of look at how you could do this. We want to get away from tree diagrams. Tree diagrams help you understand concepts. But I mean, if I did this problem with 20 objects taken 7 at a time, there's no way in the world you'd want to do a tree diagram. That's ridiculous. So the number of ways to pick the first letter. How many ways are there to pick the first letter? 3. How about the second letter? Right, there's only 2 left over. So you have 3 times 2. So you get 6 ways. Okay, so we get the same answer. So what I'm going to do is introduce you to the permutation formula of n objects taken r at a time. So on this particular problem, we're going to write this like this. P stands for permutation. We're choosing from 3 letters, but we're choosing 2 of those letters and figuring out how to list all the possibilities. Okay, well, the way this formula goes is this number. You do the factorial, so we do the 3 factorial. Then we subtract n and r, so that would be 3 minus 2. Like that. So that's how the permutation formula goes of n items taken r at a time. Now, if you work this out, you would have 3 factorial over 1 factorial. So what's 3 factorial? That's 3 times 2 times 1. What did we say 1 factorial was? we said by definition that's 1. So notice we get 6 over 1. So we get 6 ways. And in a little bit, I'll show you how to do this on the calculator. So I want to go over at the side and just show you something. Like, for instance, if you had P44, earlier I gave you the definition that that's really just 4 factorial. Here's why. When you do this formula, you would do this factorial, and then 4 minus 4 factorial. Okay, so what I'm doing is I'm applying this formula right here. So it's 4 factorial over 4 minus 4 factorial. So that's 4 factorial over 0 factorial. What was z factorial? We said by definition that's 1. So notice that you get 4 factorial. Okay? So that's the idea. So that tree diagram's kind of trying to help you understand what this formula is doing. Okay, so let's go to the next page then. And the next page just shows you this formula. We say a permutation of n objects taken r at a time. And that just shows you the formula of how that's written out. And then remember, by definition, 0 factorial is 1. Okay, so that's just the formula and how that's to be worked out. Okay, so let's see. I think what I'm going to have you do now, and let's try this. The problem that I just did, I had, 3 letters. All right, X, Y, Z. So I want you to work a little bit on this one. We have 4 letters, and we're going to take that 2 at a time. So what I want you to do is do the tree diagram first. Then do multiplication principle. And then try to use that permutation formula. So pause, see if you can do this correctly. Okay, moment of truth. Let's see if we got this right. So it turns out there's 12 ways. All right, so the tree diagram goes like this. The first letter, you have 4 possibilities. There's 4 ways to pick the first letter, A, B, C, D. Since when you get to the second letter, there's only 3 things left over. So if you chose the A, the only thing would be left would be B, C, and D. If you chose B, what's left? A, C, and D. If you chose C, A, B, and D is left. If you chose D, A, B, and C is left. Okay, so if you look at these branches, if you just started counting these branches here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The possibilities, I wasn't requiring you to list the possibilities, but it's worth writing down. To do this, you'd have AB, AC, AD, BA, BC, BD, CA, CB, CD, DA, DB, DC. Those are your 12 possibilities. Now, a couple of things I want you to notice on this too is order matters. And that's kind of an important thing on a permutation. AB is considered different than BA. All right, and if you kind of look in here, see how you have an AC and you have a CA. And you could identify this throughout this. AD, you have a DA. BC, you have a CB, and so forth. You know, BD, CD, DB. Did I get that right? Yeah, DC. So I've got everything, you know, 2 of each, but the order they're in matters in a permutation. You can't repeat, and order matters. Okay, so that's how you do that. Now, the multiplication principle, there's 4 ways to pick the first letter, 3 ways to pick the second. 4 times 3 is 12. If you did the formula, a permutation of 4 items taken 2 at a time, by the formula you would have 4 factorial over 4 minus 2 factorial. So 4 factorial over 2 factorial. Work this out like this, you'd get 12. Okay? All right, so hopefully we did that okay. All right, so I'm going to do one more example, kind of show you how we're going to do these independently of a tree diagram, and then we'll move on and talk about what a combination is. Okay, so this example 5 says in a long distance race, how many different finishes among the first 5 places are possible if 50 people are running? So what we're saying is we have 50 people that are in a race. Okay, it's like a marathon or whatever. Okay, well, there's all kinds of ways that we could put together the first 5 places in this race. So the thing about this is order matters. Okay, because, if you think about it, your first five places, I'll just give this names. Okay, let's say I'm Brad. Brad wins. Okay, and Jane and Jude and Bob and Alice. Okay, just coming up with the first thing that comes to my head. Well, that's a specific order. If I put Bob and Brad in different places, that's a different order. Okay, because we're giving the winner, Brad, we're giving that guy the gold medal, all right, and so forth. So order does matter. That's what you have to understand. So what we're doing on this then is, the order matters. Therefore, we have what we call a permutation. When order doesn't matter, we're going to talk about that in a little bit here. That's what we're going to define to be a combination. So you wouldn't want to do a tree diagram on this. You would just want to understand that you basically have a permutation. You have 50 racers, and you have 5 people who finish in a certain order. Okay? So what you want to do with this is you want to use the formula when you do this then. Okay? And I think I'll show you on this example how we can do this on the calculator. So the formula goes like this, okay? We would take the 50 factorial, and then in the denominator we just subtract to do 50 minus 5 factorial, like that. So that would be 50 factorial over 45 factorial, like that. All right, well, again, just do this. Let's just write this out as 50 times 49 times 48 times 47 times 46 times 45 factorial. Stop at 45 factorial because you want that thing to cancel out with this thing. Then you can go straight to your calculator and you can just put in 50 times 49 times 48 times 47 times 46. Get a pretty big number on this. Okay, so that is going to give you, my calculator is giving me 254251200. So there are this humongous number. There's 254,251,200 ways to just kind of randomly pick from these 50 people and put them in order in this race. That's a humongous number, for that kind of a problem. So that's the idea. Now what I want to do is I want to take a little bit of time to show you how to do this on the calculator. I'm going to go ahead and show this now. I think I have this in my notes. Maybe, at the very last page of this, I have in my notes how to do this. Where did everything go? I'm on Math 122 all of a sudden. Must have pressed the wrong button. Okay, so going back here, I'm going to go ahead and show you how you can automatically put this in your calculator. So if you'll get your calculator out, I'll take you through this. You don't have to write down the keystrokes because they're on the last page of the handout anyway. So anyway, what you do is you do 50. First of all, you put the 50 in a clear screen. Then you go Math, Probability, and then you'll find option 2 is a permutation of n objects taken r at a time. Go like that and put the 5 in. Okay, that's all you got to do. All right, and get the answer like that. And you will be allowed to do that as a student in this class. I want you to be able to know how the formula works, kind of why the formula works the way it does, but I also want you to just be able to do it the easy way with technology. Okay, so you can put these things in. A lot of times what I have you do, like on an exam, is I just have you set it up in the formula and then you just go ahead and put it in your calculator. Okay, so really like on an exam or something, I'd probably want you to write this down and that down, and you wouldn't have to go through all that. Okay. All right, so let's go to combinations. Next thing we're going to focus on a little bit here is the idea of a combination. All right, so a combination of a set of n distinct objects taken r at a time without repetition, again, there's no repeating, is an r element subset of the set of n objects the arrangement of the elements in the subset does not matter. Okay, so that's what makes it different than a permutation. You're looking at when order does not matter. So in other words, like if you were to look at the previous example here, going up here, we would consider AB and BA to be the same thing. We'd consider AC and CA to be the same thing if it were a combination. So you might want to write down just a note of that. So you would just say something like AB is considered in a combination to be the same as BA. And as we learn these problems, we'll kind of come up with some examples of things that are combinations. Okay, so in this particular problem, what we're going to do is we're going to do a tree diagram, and I'll show you how this makes this a little bit different, right? Okay, so we're going to do this one as a combination, all right? So we're going to go ahead and start this out with a permutation, and then down here in part B, I'll show you what we do with the combination. Okay, so we're going to redo the problem that we just did a while ago. We're going to do 3 letters taken 2 at a time. Okay, so let's just kind of get this put together. So the first letter, you could choose either an X, a Y, or a Z. If you were doing a permutation, order would matter. Okay, so if we went to the next thing, the second letter, just like we did before. If we already chose an X, what's left over? Y or Z? If we already chose a Y, what's left over? X or Z? If we already chose a Z, what's left over? X or Y. So that's a permutation, right? So the possibilities would be listed like this. We would say XY, XZ, YX, YZ, ZX, and we would say ZY. Okay, so there are 6 permutations of 3 objects taken 2 at a time. All right, so that's how that goes. Okay, and notice on this, order matters, so we think of XY as being different than YX. We think of XZ as being different than ZX. And we think, what else is left over here? YZ is different than ZY. Okay, so it's totally different if it's a combination. So if it's a combination, then we would consider this. We would consider this. We're not going to count that because we've already got an XY. XZ, well, we're not going to use that. YZ, we're not going to use that. So we'd have 3 things left over. So if we're doing a combination, order does not matter. So that means the possibilities, there's a smaller number of possibilities, we'd be just left with XY, XZ, or YZ. Okay, we wouldn't count those things. We would, the XY, YX, we wouldn't count AB, BA as a different possibility. So what we end up getting is we get 3 combinations. Okay, and that's how that goes. Now now you're not always going to end up with half. I mean, sometimes students see this example and think, okay, 6 permutations, 3 combinations. It depends on the situation. Okay, so you don't want to jump to conclusions there. All right, so that's the idea. All right, so that's how we would go with that. So actually, what happens is the XY counts, the XZ counts, and then the YZ counts. Everything else is, we don't count. Okay? All right, so here's the next page, the theorem about combinations. So we have a formula. So the number of combinations of indistinct objects taken at a time without repetition is given by this formula. So we write the letter C to represent a combination of n items taken at a time. You'll also see me use this most of the time, the parentheses around the number. So like this would be 52 taken 5. Okay, we're like in a deck of cards, there's 52 cards. You're playing poker, you get a 5-card poker hand. that turns out to be a combination of 52 cards taken 5 at a time. Okay, so that's how that goes. So basically what it is it's the permutation formula divided by r factorial. So if you kind of look in the example we did here, is we divided out the 6 divided by 2. All right, so you're going to kind of make that connection as we go through there. We divided out the possibilities that were backwards, like x, y, y, x, like I was saying. Okay, so the formula is going to go like this. The one you're going to look at mostly is not this one so much as this one. So you do n factorial over r factorial, n minus r factorial. One thing I do want to point out, this thing right here that I'm highlighting in green, that part right there is the permutation formula. Okay, n factorial over n minus r factorial. If you back up a couple of pages, see right there, that's the permutation formula. So the only difference is you divide by that r factorial. So on this problem, what we ended up doing is the r factorial would be 2 factorial. All right, so that's how that goes. So actually, in the difference between this problem, this one would be permutation of 3 letters taken 2 at a time. So we would say 3 factorial over 3 minus 2 factorial. The combination you would write like this. You would say C, 3 letters taken 2 at a time, and this would go 3 factorial over 2 factorial times 3 minus 2 factorial. So if you look at the difference between those two things, that's ultimately how you get that answer to the problem. And it turned out that 2 factorial is 2. That's why we ended up getting half the number of combinations. Okay. Okay. So let's use that formula on the problem we just did. So the problem we just did, we had a combination, 3 letters taken 2 at a time. So the formula goes like this. This is your n factorial. So we'd say 3 factorial over r factorial, which is this number. And then we subtract those two in this order. So 3 minus 2 factorial. So that's how that gets put together. So that would be 3 factorial over 2 factorial times 1 factorial. So that would be 3 times 2. You could just write that like that. Leave that alone. Now remember, 1 factorial is just 1. So that would cancel out. You would have 3 over 1. Therefore, you would end up with 3 combinations. Okay, so that's how it works out. The way this goes on the calculator, I'll go ahead and show this to you now, is if we do the problem that I just did, we would put in the 3 in a screen, do that first, then go math, probability. Now you go option 3, which is a combination. Then you put in the 2, then you get the 3. Okay, so that's what you end up getting. Is you can easily do these things on most scientific calculators, and all of the graphing calculators are going to have this built in. Okay, so let's take a look at some examples here. And mostly what we're going to do is set up the formula, write the formula out, and then go to the calculator. Okay, so let's look at this. The key thing on this always is when you're given a problem, you're always going to be choosing from a list a certain number from a list. You know, in this case, you're choosing from 7 people, you're choosing 3 people. You have to ask the question, does order matter? If order matters, and this is real big deal, this is what it's all about. If order matters, then you have a permutation. Okay, if order does not matter, and you have to think about that and figure that out. So if order does not matter, then what you have is you have a combination. And I'll give you some illustrations of kind of some things that will kind of help you understand that better. Okay, so example 7 says, how many ways can a 3-person subcommittee be selected from a committee of 7 people? So we have to ask the question, does order matter? All right, well, let's just say that our 7 people, let's just give them letters. A, B, C, D, E, F, G. Okay, first 7 letters of the alphabet. Okay, now what we're doing is just randomly picking 3 people and putting them in a committee. So the question we have to ask is ABC the same as BCA? Remember, all we're doing is just selecting from 7 people and putting them in a committee. We're not giving them a job. We're not like saying, you're the president, you're the vice president, you're the treasurer. So since we're not giving them jobs, then order does not matter. Okay, so if I chose Amy, Brad, and Craig, it doesn't matter what order I chose them in, it's still my committee. So in this case, order does not matter, therefore it's a combination. Okay, that's what you got to kind of think about. You got to get that idea. Now, see what I'm going to do in part B is I'm going to give those 3 people jobs, so then the order does matter. So this is a pretty good analogy, I think, to help you understand that. So anyway, what we'd do is we'd say, okay, it's a combination. Order didn't matter. We're choosing 3 people from 7. So the formula goes like this. We do 7 factorial over 3 factorial, and then we do 7 minus 3 factorial like that. Okay, let's write this out. So this would just be 7 factorial over 3 factorial, 4 factorial. So I'm going to write this as 7 times 6 times 5 times 4 factorial over 3 factorial, 4 factorial. And what that'll do is that'll get that to cancel out. And then you could do this on your calculator. So this would just be 7 times 6 times 5 over 3 times 2 times 1. So you can do that if you want to, and then you could do 7 times 6 times 5, which is, what the heck? 7 times 6 times 5 is 210. Divided by 6. So that would be 35 ways that you could put that together. Okay? And again, what I want you to do is to be able to write that down, and maybe that, and then just go to your calculator. So what you can do now is, without going through all this, if you want to, I'm perfectly fine if you just do the rest like this. You could just go 7 math, probability, option 3 is a combination, taking 3 at a time, and there's your answer. Okay. All right, so there's 35 ways to put that together then. Okay, so now in the next part of this, we're going to look at how many ways can the 3 people we choose be a president, vice president, and secretary. So the idea with this would be, okay, you got the president, you got the vice president, you got the secretary. So if we had ABC and then BAC, see, that's different. So order does matter. Okay? It depends on, if you're assigning these people specific jobs, order matters, so therefore it's a permutation. Okay, that's what you got to understand. It's how to know which is which. All right, so this is a permutation. So we would do a permutation of 7 objects, taking 3 at a time. All right, and what we'd have on this is a permutation formula goes, you take that number factorial divided by the difference, 7 minus 3 factorial. You don't put in the divide by 3 factorial like you do in a combination. So that's 7 factorial over 4 factorial. So that is 7 times 6 times 5 times 4 factorial over 4 factorial, and that'll cross that out. So then you could go to your calculator, and that would be, I think, 210. You can do that in your head. All right, let's check and make sure it's right. So we'll just do 7 math, probability, permutation, and then put in the 3. Okay. All right, so that's how you do that. So the key thing when you're learning this, again, is how do you know when order matters? That's what you have to kind of think about as you're piecing this stuff together. Why does it keep doing that? I do not want it to do that. Okay, so anyway, you see how I did that on the calculator. Okay, so we're going to go to the next page. I'm going to let you do this problem. Just read the problem, think about it, see what you come up with. Okay, so go ahead and pause, work it out. Okay, so just check your calculations, see if you did this right. Now, this time I told you whether order mattered or not, so I kind of made that a little bit easier for you. So on this first one, order is taken into consideration. Order matters, therefore it's a permutation. So you would be doing a permutation, 9 things taken 3 at a time. If you did that on the calculator, you get 504 automatically. This is the setup. You want to look over that, make sure you did that okay. Part B, I said order is not taken into consideration. So that would be, excuse me, I'm putting myself to sleep. So combination, order does not matter. Okay, so we do that. That's combination, 9 things taken 3 at a time. So 9 factorial over 3 factorial, 9 minus 3 or 6 factorial. So you get 84. You can look through the details of how that got put together. Okay. All right, so let's see. Now we're going to go on, talk about some card problems. Those are always good problems to show students. Okay, so we're going to look at a standard deck of cards and kind of get this put together. So if you're not a card player, it's easy to learn how cards go. So there's a total of 52 cards. These are kind of the key things that you want to know. There's 4 suits. These are the hearts. These are the diamonds. Those are the clubs. Those are the spades. And there's 26 are red. 26 are black. And then the face cards are these right here. Aces are not face cards. So those are the 12 face cards. So if you're not a card player, you can go buy you a deck of cards and at least learn how the numbers go and everything. In general, for this level of a class, I'm not requiring that you learn how to play poker or anything. So generally what I do on an exam is I have students from time to time who've never even had a deck of cards in their entire life. So I just give this picture, and you need to be able to know this information here, okay? So as we go through these problems on the next page, we're going to put this together. So I'm going to pause just for a minute and take a screenshot of this because it'll be helpful when I'm teaching. Okay, so I wanted to just set up this picture so as I'm going over these examples, we can refer to this. Now, first of all, if you're dealt cards, like for instance, this first example says from the 52 card deck, you're choosing 6 card hands. So the idea would be, like if you were dealt, let's just keep it simple here. Let's just say that you were dealt these 6 cards. Now, it wouldn't matter what order those cards are in. It's still the same poker hand, and that's not even a poker hand. You'd probably want to trade in some cards on them. All right? So, it doesn't matter. Order does not matter when you're dealt a hand. It's the same thing. So, if order does not matter, then which is it? Is it a permutation or is it a combination? That's what you got to get in your mind. If order does not matter, it's a combination. So these problems are going to be combination problems, okay? A deck of cards is a good analogy for you to have in your mind of what combinations are. If I give you 5 cards, it doesn't matter what order I give you those 5 cards. It's still the same poker hand, okay? If you play poker, you know what I mean by that, right? Okay? If I deal you the 5 cards that make up a royal flush, it doesn't matter which order I give those cards to. It's still a royal flush, right? Okay, so here's what we do on this. Okay, we're going to find how many 6 card hands consist of entirely red cards. Okay, so here's the idea. So first of all, what we're doing is we're choosing 6 cards, but all of those cards are red. So how many cards are red? There's 26 red cards. So you're choosing the 6 from the 26. You're not choosing 6 from 52. because we're not considering these black cards. So this would be a combination chosen from the 26 red cards, 6 at a time. Okay, like that. Well, let's just put this in the formula. Now we're going to use our calculator. So we got 26 factorial over 6 factorial times 26 minus 6 factorial. And then that's going to be 26 factorial over 6 factorial, 20 factorial. Now from here, just go to your calculator. On an exam, typically I want you to show this formula and then just go to your calculator. All right, so just put this in like this. Put in the 26, math, probability, option 3, taking 6 at a time, and that'll give you this. So that's how many poker hands are possible. So that answer would be 230,230 poker hands consisting of all red cards is what you would end up having. If you don't believe me, get your deck of cards and spend the whole weekend sorting out all of those possibilities. Okay, that's what it is. That the math isn't lying. Okay, so that's the idea there. Now we're going to push on, just kind of keep looking at these. This says, from a 52 card deck, how many 6 card hands consist entirely of clubs? Well, okay, how many clubs are in a deck? That's what we're choosing from. The clubs are these. There are 13. Okay, count that out. You got 9, 10, 11, 12. So you have 13 right there. All right. Those are your 13 cards. Whoops, I missed the ace. There we go. Okay, so there's your 13 cards right there. All right. So we're going to do this. We're going to take a combination. We're choosing from 15 clubs, 6 cards. The 52 is irrelevant in this. There's 52 cards in the deck, but what you have to know is the 13 of those are clubs. So this would go like this. We would say 13 factorial over 6 factorial, 13 minus 6 factorial, so that would be 13 factorial over 6 factorial, 7 factorial, then just go straight to your calculator, okay? So on a clear screen, we'll do 13, math, probability, option 3, combination 6 at a time. So there are 1,716 6-card poker hands that consist of all clubs. So if you play poker, that's a good hand. If you get all clubs, that's called a flush. So there's a smaller number of possibilities on that, right? So that's how we figure out which poker hands are the most valuable, is based on how many possibilities there are and what the probabilities are. All right, so we got that. And then the next example is from a 52 card deck, how many 5-card hands consist entirely of face cards? Okay, well, what you have to know on this is what the face cards are. So there are 12 face cards. The face cards are Jack, Queen, King, and for each suit, those would be your 12 face cards that I say there. So what this is going to be is a combination, choosing from the 12 face cards, 5 cards. Now, you'll see me write this a lot this way. You can also just write a combination that way. Can't do a permutation that way, but the shorthand notation you can write in parentheses. So this goes like this. It would be 12 factorial over 5 factorial. 12 minus 5 would be 7 factorial. And that's good enough. You just write that, then we go straight to the calculator. So we'll put in the 12 face cards, math, probability, combination, 5 card hands. So there are 792 possible hands, 5 card hands that would have nothing but face cards in it. Okay, so that's the idea. All right, and then one last example here, or a couple of more examples, I guess. Okay, I'm going to move this down just a little bit here for reference. And, you know, when you're working your homework out, if you need this diagram, you can go on the internet and Google cards, and you'll see images, this same image. I got this picture from the internet. Okay, so this next one says, from 52 card deck, how many 7 card hands contain 4 kings? Okay, now this one gets a little bit harder now. So, all right, there's, first of all, how many kings are in a deck? There's 4 kings in a deck. So the idea with this is, this one's going to be a little bit trickier for most students to do. So first of all, you are getting 4 kings. Now that's going to be 4 taken 4 at a time. Okay, there are 4 kings that have to be chosen from the 4 kings in the deck. Okay, so that's what that is then. All right. In fact, there's only one way to do that. All right. But what's left over? Okay, now see, we have a 7-card poker hand. So that means if we've already got 4 kings, then how many leftover cards go here? Okay, there's 3. If we've already chosen 4 cards here, how many are left over? So I've already taken those out of the deck. What's left? Not 52. 52 minus 4 would be 48. And you have to multiply that together by the multiplication principle. So you'd put this together like this. Now what we're going to do on this is when we put this together in the formula, this would go like this. This would be 4 factorial over 4 factorial and then 0 factorial. Just by using that. 4 minus 4 is 0. So that would be that first thing. The second thing would be 48 factorial over 3 factorial, and then 48 minus 3 is 45 factorial. Okay, and that's good enough. From here, we're just going to put this in the calculator. So let's put this together kind of like this. Okay, so clear screen. What we're going to do is this. We're going to do parenthesis, 4 math, probability, combination, 4 at a time. That's 1. There's only one way to get 4 kings out of a deck. And then times. You can put the times sign in or leave it off. Then go 48. And then math, probability, combination, and 3 like that. So that's how you put it in your calculator, and that gives the answer. All right, so that would end up giving us the number of possibilities of getting a 7-card hand that contains 4 kings. So there's 17,296 ways to get 7 cards out of a deck that have 4 kings. Okay, the other 3 cards are anything. That's why you got so many possibilities there. Okay, so that's it. All right, that's a little harder one to do. All right, let's read this next one here. So this next one says, from a standard 52 card deck, how many 7-card hands consist of 3 hearts and 4 diamonds? Okay, so here's what we got to do. The first thing is, out of these 7 cards, 3 are going to be hearts. How many hearts are there to choose from? Okay, well, how many hearts are there in a deck of cards? There's 13. There's your 13 hearts, and you are choosing 3 hearts. Okay, you're not taking from the 52, you're taking from the hearts, because I'm telling you, you're getting 3 hearts. Then it says you're picking 4 diamonds. Well, how many diamonds are in a deck? It's also 13. Okay, like that. And then you'd multiply it together. Okay, this adds up to 7 already. So we've got our 7 cards. It's just 3 come from hearts and 4 come from diamonds. Okay, now this one, let's just put this totally in our calculator. We don't have to write anything out on this. I'm just going to go like this. Parentheses, 13, math, probability, combination, 3 at a time. Okay, you can leave the parentheses off. That means multiplication to the calculator. 13, math, probability combination 4, like that. Put that in, and then that'll tell you the magic number. So that is, what is that, 204,490 ways. So what that means is if you reach into a deck and pull out 7 cards, there are 204,490 ways to pick 7 cards, where 3 of them are hearts and 4 are diamonds. The math don't lie. Okay, that's the truth. All right, so that's it. Now the last page is just to show you how to do this on the calculator. So that'll wrap up the information you need to do on this. Really, the key thing is when you're doing your homework and stuff is you have to usually decide whether you're dealing with a permutation or combination. The big deal is a combination order doesn't matter. Use cards as an analogy. Cards, when you're dealt cards, order doesn't matter. A permutation order does matter, so the analogy you should use on that is a race. Okay, like, okay, I got 50 people in a race, one person gets the gold, one gets the silver, one gets the bronze. Order matters. Okay, so that's a good example, all right? And once you get the hang of that, it's just a matter of getting it set up, and be sure that you know how to do this on the calculator and know that well. Save you a lot of time. All right, so good luck. Hope that helps you to learn this information.